Swayam Prabha. Digital India. Educated India.
So, we move on to the second lecture of the course, where we continue the discussion that we began with in the first lecture. So, we will continue with the introduction to supersonic and hypersonic flows, and in the second lecture let us try to have a brief review of topics that would be covered in the first few weeks of this course, and there would be a recapitulation of basics of compressible flow and thermodynamics, which will be necessary in order to make this course more meaningful. So, let us begin with all that. If you look at the contents of this course over the next 2 weeks, what are the things we plan to learn in this course? Let us try to have an overview on that. So, in week 2, we will look at governing equations of inviscid compressible flow. If you may recall from your earlier exposure of fluid mechanics, then that in inviscid compressible flows we basically deal with Euler equations, and when we make certain simplifications, idealizations, we may be talking about the velocity potential equation, and we can talk about small disturbance equations and local surface inclination theory for supersonic and hypersonic flows. That is when we simplify the governing equations on the basis of small perturbations. That means we talk about slender geometries like a flat plate at a small angle of attack, and we try to find out how the governing equations may get simplified if we impose the assumption of small perturbations. And then we also would try to look at some theories where inclination of the surface, say the angle of attack of the flat plate, is used to obtain the pressure distribution on it. So, these are some of the things we plan to do in the week 2 of the course. In the week 3, we will begin with a brief introduction to waves. As we all know, compressible flows manifest wave-like behavior. We come across normal and oblique shocks, we come across expansion waves. Therefore, we look at both compressive and expansive waves, and we try to look at where these waves are formed or where do they occur. Shock and expansion wave relations in the high Mach number limit. Since this course deals with the supersonic and hypersonic regimes both, it becomes imperative for us to look at the different relations which govern shock and expansion waves over a wide Mach number regime. And this becomes relevant when we try to use the equations which are normally derived for the supersonic regime. How can they be extended at much higher Mach numbers, and what is the implication? In these compressible flows where you have abundance of wave-like features, you can think about different kind of interactions occurring. Some of the more common ones are interaction between shocks, where we say it is a shock-shock interaction. There could also be interaction between shock and vortex. So, these are very interesting phenomena which we will briefly look at. Now, it is imperative that this is a good time to start recapitulating your earlier lessons on both basic thermodynamics and compressible flows to make the learning in the upcoming weeks smoother and more relevant. So, that will make the meaning of this course more significant, we look at basic thermodynamics concepts, and to begin with we look at the perfect gas assumption that we often begin with, where we consider the gas is comprised of a large number of molecules, but the intermolecular forces are negligible, which means that the molecules are not very close to each other. And then we talk about the equation of state for a perfect gas, where the equation is given by small p times capital V is equal to RT. That's what you can see over here. And here the R is a capital R, which represents the universal gas constant, given by a value of 8314 joules per kg mole Kelvin, which is identical for all kinds of gases. V is the molar volume in meter cube per kg mole. So this is a very important equation that we always have to remember when we deal with compressible flows. You can represent this equation in a different form. P times small v is equal to RT, where the R happens to be a specific gas constant. So we are not using a bold R here, unlike the earlier equation where the bold R represented the universal gas constant. And if you talk about air as the medium, then this R turns out to be 287 joules per kg Kelvin. So that's another very important value that you should keep in mind. The small v stands for specific volume, which is the reciprocal of density and therefore has units of meter cube per kg. And of course, the capital R used in the second equation, which is not the bold R, is given by this equation, where we can see it's the ratio of the universal gas constant and the molecular weight of the gas. These are very, very important equations which you should be comfortable with. And when we look at the medium, we look at it both from a microscopic viewpoint as well as a macroscopic viewpoint in thermodynamics. So from a microscopic viewpoint, we look at it as a collection of particles in random motion, and individual kinetic energy of each particle contributes to the overall energy of the gas. If the particle is a molecule, it comprises of multiple atoms. It can have different kinds of energy modes comprising of rotational, vibrational motions, not only translational motion. And additionally, they would also have the electronic energy coming by virtue of the motion of electrons in both atoms and molecules, which contribute to the source of energy. So all put together, the energy constitutes the specific internal energy of the gas, the small e per unit mass. The system comprising of gas particles is in equilibrium when the particles are in a maximum state of randomness. So this is the molecular or microscopic viewpoint, and we often deal with details of all this in microscopic thermodynamics. The classical thermodynamics deals with the macroscopic viewpoint of the gas, which deals with it as a continuum. Equilibrium exists when there are no gradients in velocity, pressure, temperature and chemical concentrations throughout the system. This means that under equilibrium the system has uniform properties, and for an equilibrium system of a real gas where intermolecular forces are important, and also for an equilibrium chemically reacting mixture of perfect gases, the internal energy is a function of both temperature and volume. Similarly, it is true for enthalpy, and we try to show that mathematically in the equations below. For both a real gas and a chemically reacting mixture of perfect gases, these expressions hold good. So these are important facts which you should be aware of. Let's move on to the next slide. If the gas is not chemically reacting and if we ignore intermolecular forces, the resulting system is a thermally perfect gas where internal energy and enthalpy are functions of temperature only, and where the specific heats at constant volume and pressure, which we call as Cv and Cp, are also functions of temperature only. So, the thermally perfect gas assumption should be clear to you. If the specific heats are constant, the system is a calorically perfect gas. In many compressible flow applications, the pressures and temperatures are moderate enough, and therefore, the gas can be considered to be calorically perfect. So, Cp and Cv then becomes constant in a calorically perfect gas. Further, for a calorically perfect or a thermally perfect gas, the following relations hold good, which we can see below. So, all these relations are important. So, here we are talking about the temperature dependence, here we are talking about constant Cv and Cp, and then we are talking about the difference between Cp and Cv over here, which is giving us the R, and we are expressing Cp and Cv as partial derivatives of enthalpy and internal energy, specific internal energy with respect to temperature for constant pressure and constant volume situations. So, these definitions are very important while defining Cp, Cv and their relationships. Again, as I said a few minutes back, it is a good time for you to recapitulate all this by going through some basic texts of thermodynamics as well as compressible flows, which will give you a very good starting point for this course. Let us move on to the next slide. Let us have a quick recap of the laws of thermodynamics. As you may recall that the first law of thermodynamics is written for a closed system using a statement like what is on the left, del Q plus del W is equal to dE. In this equation, E is a state variable, hence dE is an exact differential. So, small e is essentially the internal energy, the specific internal energy that we have been talking about. Its value depends only on the initial and final states of the system, and in contrast, del Q and del W depend on the process or path followed in going from the initial to the final state of a thermodynamic process. For a given differential change in internal energy, there are in general an infinite number of different processes or ways by which heat can be added and work done on the system. The three main types of processes which are encountered are given as 1, 2 and 3 respectively. The adiabatic process, where no heat is added to or taken away from the system, and in such a process del Q is equal to 0. A reversible process, where no dissipative phenomena occur in the process, which can lead to irreversible effects. Effects of viscosity, thermal conductivity and mass diffusion are absent in such process. Therefore, we do not talk about momentum transfer or heat transfer or mass transfer under finite gradients there. Isentropic process, it is both adiabatic and reversible. For a reversible process, del W can be given as minus P dV, where dV is an incremental change in specific volume of the system due to a displacement of the boundary of the system. Now, since the isentropic process is adiabatic, therefore, del Q is 0 and therefore, the statement would be that minus P dV is equal to dE. If you look at the second law of thermodynamics, the equation is given on the top left, that ds is equal to del Q by T plus ds irreversible. As you may recall that all path dependent variables are indicated by del, while the state variables are defined by d based on inexact and exact differentials. Now, this equation states that the change in entropy during any incremental process is equal to the actual heat added divided by the temperature, which is del Q by T, plus a contribution from the irreversible dissipative phenomena of viscosity, thermal conductivity and mass diffusion occurring within the system. Additionally, entropy increases for chemical reactions occurring under non-equilibrium. This is something that we will elaborate on in a later week's lecture. These dissipative phenomena will always increase the entropy, hence the ds irreversible part of that equation will be greater than equal to 0. For a reversible process only, ds irreversible is equal to 0. So, for a process, it will always proceed in a direction such that the entropy of the system plus surroundings always increases or at best stays the same. This is the bottom line. Now, based on this discussion that we have already done, we can write from the original equation that ds is greater than equal to del Q by T for adiabatic process, ds is greater than equal to 0. And then if you talk about a reversible process, then you can put it as TdS minus PdV equal to dE, because you are replacing the first term based on the del Q reversible, and then TdS can be written as dE plus PdV, and then using the equation H is equal to E plus PV, that means the relation connecting enthalpy with internal energy and the product of P times V, we can further represent it as TdS is equal to dH minus VdP. So, all these equations you should be very comfortable with, because you have to handle all these equations elaborately in this course, and it is a good time to revise all that. If you integrate these relations, you should be able to come to the equation that we see at the bottom of the slide, where we talk about the entropy change between the end state 2 and starting state 1 for a calorically perfect gas. Now, calorically perfect gas assumption is fine usually in the supersonic regime, but that is a questionable assumption when we look at hypersonic flows. So, that will be elaborated later. Isentropic equations for calorically perfect gas can be derived from the condition that ds is equal to 0, and therefore, from the equation that we had integrated, we can derive the condition that we show in the blue box to begin with, and then it branches off into the equations that we write on the two red boxes on the left and right, and finally it converges to what we have in the green box in terms of the pressure ratio, density ratio and temperature ratio getting connected with each other, with the gamma often appearing in the indices. So, these are equations that you should try deriving on your own as a homework. So, that was a little discussion on equation of state, followed by the two laws of thermodynamics, the first and the second law. And then if you look at governing equations of the flow field, like we were saying that when you deal with compressible flow fields, you should be kind of conversant with the governing equations. Though we will be discussing in the subsequent weeks, it is always better to get yourself familiarized before we go into the details. So, the velocity potential equation is one of the most fundamental equations in this domain, and it all starts by looking at a three-dimensional velocity field in a compressible flow, where the vector v can be split into three Cartesian components, small u, small v and v, small w, written in a vectorial form. And in the second line, you find a very important equation written in a very compact form, the Euler equation. It is a connection between pressure and velocity changes in an inviscid compressible flow, and the statement happens to be dP is equal to minus rho v dV. This is one of the most important relations in the fluid dynamics world. And then we impose the constraint when we try deriving the velocity potential equation, we impose the constraint that the flow has to be irrotational. So, the condition for irrotationality of the flow comes from the curl of the velocity vector. Curl V is given by the three terms in the bracketed form that we can see over here. Those form the three components of the curl of velocity vector, and the condition of irrotationality says that they have to be individually equal to 0, and the velocity potential would exist only in irrotational fields. Therefore, the capital phi would exist if it is an irrotational compressible flow. We further bring in the continuity equation, and in its steady form it is shown by the divergence of the product of rho times v, and then it can be expanded in this form, and then if you replace the velocity components in terms of the derivatives of the velocity potential, then you come up with a form like this. So, I hope most of you are able to recall some of these basic ingredients of fluid dynamics which you must have come across in some earlier courses. If you haven't, or if you don't recall very well at this point of time, it is a good time to recap all that as a bit of homework, so that you are more comfortable with the later parts of the course. So, let us move on, and then I leave it as a small homework for you to come to this final form of the velocity potential equation as a little bit of a exercise that you can do at home. And you see that it is actually a nonlinear partial differential equation in capital phi involving second order derivatives of phi, and it also involves square of the sonic speed, and there is a separate equation written in a lower box, a square, which gives you the expression of the sonic speed. Therefore, they have to be solved in a couple manner, and this equation in phi, it applies to any irrotational isentropic flow for all ranges of Mach number, and that is very interesting. It covers from the supersonic to hypersonic regime that we are talking about in this course. It also covers compressible flows in the subsonic or transonic regime, as long as it satisfies the conditions which have to be fulfilled. It also applies to incompressible flow where A tends to infinity and yields the Laplace equation, which is at the bottommost box, the Laplacian phi equal to 0 equation. Next we move on to a very important question, that what is a shock wave, and this is a bread and butter of compressible flow, and we will discuss about it at length in this course. And we have two sketches on the top left where we see a normal shock and an oblique shock, and we see many of the properties jumping abruptly across the shocks. And another interesting fact is that in oblique shocks, the Mach number behind the shock may remain supersonic, while it is always subsonic in the case of the normal shock. However, the normal component of the flow across the oblique shock behaves identically as a normal shock. So, these are very important facts which if you are not comfortable yet, it is good time to familiarize yourself. And at the top middle portion, we have tried defining a shock wave in some manner in the box, followed by some sketches on the top right where we have tried representing formation of shock waves through coalescing of characteristics in the flow field. As you may be knowing that these compressible flows are basically governed by hyperbolic partial differential equations, and hyperbolic partial differential equations manifest real characteristics, and when the characteristics diverge, they form expansion fans. When they converge, they form shock waves. The perturbations or signals propagate along these characteristics, and these characteristics are shown in xt plots. So, the top right plot is trying to give you some idea about how characteristic curves look like in the xt plane. They are usually given by a form dx dt is equal to some function of u and a, as you can see in some of those plots. So, this would be interesting for you to review and explore. We will try to elaborate on these things as we move along the course. And as you may recall that in the previous slide itself we talked about normal and oblique shocks. We also earlier have talked about expansion waves. So, essentially when we talk about shocks, we say that these are strong compressive waves and they create some kind of discontinuous jump of certain flow properties. And again, interestingly, some of the flux values remain conserved across normal shocks, especially when we derive the conservation equations of mass, momentum and energy. We see that the fluxes are nicely conserved across such discontinuity, and normal shocks can form inside a cylinder within which a piston is moving rapidly. It can form near the nose region of blunt objects in supersonic and hypersonic flow, and expansion of high pressure gas inside converging diverging nozzles or ducts. Usually if you see shocks, you will see in the diverging portion of CD nozzle or near to the exit of the nozzle, or you may see oblique shock formed at the exit, which comes next. So, when a supersonic flow is turned into itself, that is when it encounters a corner across which the body surface tilts upwards to the flow direction, it leads to formation of an oblique shock. Such a corner is often called as a compression corner, because it compresses the flow and raises its pressure and decelerates the flow. The flow field across an oblique shock is two-dimensional, and it is a weaker shock compared to the normal shock. On the contrary, when a supersonic flow is turned away from itself, when it encounters a corner across which the body surface tilts away from the flow direction, an expansion fan is formed at the corner. The pressure reduces, the flow accelerates, and the flow behaves in an isentropic manner as it expands, unlike shocks where the entropy always increases. So, these are certain normal shock relations where the downstream properties can be expressed in terms of the upstream Mach number and the gamma. These are again equations which you might have come across, might have learned earlier. It is a good time to brush them up. So, we finally try concluding that in this lecture we started a brief review of thermodynamics. We had a preliminary discussion on basics of the equation of state, the laws of thermodynamics, velocity potential equation and shock waves. So, this was a very preliminary discussion, of course, and many of the thoughts and equations that we looked at them very briefly in a very concise and precise manner, just to make you recall that some of this might have been taught to you in earlier courses. So, it's a good time for you to recap all this, because this would be a bread and butter of this course. Thank you.